So, this is the course webpage. I think I went over this last time. Oh, okay, I should have updated the course syllabus, but I didn't, okay, because you know what? I was still kind of thinking about, we'll go by the lecture number right now, because I'm like, you know, I'm a little disoriented, okay? As maybe some of you are also. So the first, I did intro, so we're going to have a few lectures on probability, okay? Then we're going to talk about causal Gaussian models. You'd say, okay, so I don't know. Maybe some of you may feel that the material in this class may feel a little abstract, okay? But I do want to point out that it's really quite useful for a lot of problems. I mean, this is pretty practical stuff, okay? It's just the way I present it maybe doesn't make it look that way so much, because I'm not emphasizing sort of applications and data, real data. Because when you get into real data, things kind of get complicated. So we kind of do idealized cases in this case. But this stuff is really used for a lot of different applications. Maybe I should have said something about that, because it may not be obvious to you, the motivation. You know, it's obviously used for a lot of medical imaging problems, in medical CT, for example. But it's also used in a lot of scientific imaging problems. Like, you know, some of you, I'm sure, know about this. Things like electron microscopy. There's a lot of synchrotron imaging. I know there's at least one material scientist in here, but like a lot of material scientists use this kind of technology. Synchrotrons are really kind of interesting. That there's about 5 or 6. There's about 6 maybe in the country. Something like that. Maybe, let me see. There's Lawrence, there's Argonne National Labs is over here in Chicago. And it has a thing called the Advanced Photon Source. And then there's the Advanced Light Source. That came after the Advanced Photon Source, so they had to give it a different name. And that's at Lawrence Berkeley National Labs, which is right up the hill from Berkeley ECE department, ECS department. And then there's the CHESS, which is the synchrotron at Cornell. And there's SLAC, which isn't a synchrotron, but it's sort of similar at Stanford. SLAC is the, what does SLAC stand for? Does anybody know? Okay, it's the something. It's the free electron laser, I think is what it is. Okay, it's basically a linear, it's a different kind of technology, but it kind of achieves a similar result. It's more coherent. And there must be other ones, but here's the sort of the story about what synchrotrons are. It's kind of interesting. I'm a little off topic, but what the heck. I don't want this to feel like so antiseptic, okay? That it's not disconnected from reality. So synchrotrons are, yeah, synchrotrons, what they did is, and they, synchrotrons, you know, everybody knows about the LHC, right? The Large Hadron Collider. So, you know, to do particle physics, they kept making bigger and bigger colliders to get various particles to collide, and then with greater energy, you can create bigger particles, basically, because of the relationship between energy and mass, right? E equals mc squared. So, if you want to, like, do particle physics, and discover these particles, you build colliders. But the first colliders they did, well, okay, first, this is physics history from a signal processing person, so, you know. But they start off with cyclotrons, okay? And a cyclotron is basically the electrons just go around in a circle, okay? So basically there's a big magnetic field, and it's just like a merry-go-round, right? It just goes around in a circle. And cyclotrons are really commonly used for medical applications because they use them to make isotopes like F18 that we'll talk about for PET. F18 is used in a thing called FDG. So if you get a PET scan, most PET scans are based on FDG, which is fluorodeoxyglucose. And it's basically they take glucose and add F18, which is an isotope of fluorine, to it. And then it's radioactive, so that's how they image you in the PET scanner. But cyclotrons are nice and compact, so you can have a cyclotron that's like, you know, sort of the size of a few large washing machines, you might say. So, you know, they can have them in-house. but that you can only get such high energies. And the synchrotron, what they do is they have essentially like a polygon. They have more sides than this, but like that. And at each of these vertices of the polygon, they have a magnet that bends the beam, right? And then they get these, and then they make the synchrotrons really big. So the synchrotrons are like, if you take, I should show a picture of a synchrotron, but they have like aerial views from a UAV of Lawrence Berkeley, of the APS at Lawrence Livermore, Oregon National Lab. And it's like, you know, this huge building, okay, that is like circular, okay? And so this might be like a football field in diameter or something. And then they bend the beam, and these electrons get going really fast, so they have higher energy. But the problem is that these synchrotrons that they built were wonderful, except for now they're all sort of rendered obsolete by the Large Hadron Collider. You can't really do very interesting particle physics. So they kind of repurposed them, because they noticed when the electrons were going around this thing, that when you accelerate them here, where the magnet is, when you accelerate an electron, you accelerate charge, what happens? Do you know? How many people are electrical engineers in here? Okay, so any electrical engineer should know this, but of course you probably don't, so don't feel bad. But if you accelerate charge, what happens? It creates, you emit energy, right? An electromagnetic photon. You emit photons. So like when, so actually, for example, in an X-ray scanner, you have a tungsten target, and well, actually, the way it's usually done is like this. And the electron beam hits the target, and the photons come out perpendicular because of the right-hand rule, okay? So, so in the old TV sets, CRTs, people like worry about getting irradiated, but as long as you stand in front of the TV, you're fine. It's if you're on the side of the TV that you would have photons hitting you, X-ray photons. So when you accelerate, I mean, this is like, you know, Maxwell's equations say dE dt, you know, results. There's a cross product in the Maxwell's equations, okay? Anyway, so what happened is that when they accelerate these things, they produce photons. Oh gosh, which way did the photons come out? Maybe they come out this way, actually. I'm not really sure. Okay, I should know. Okay, and so at each of these points, they create what's called a beam line. And they might have about 20 beam lines, because they get a very intense, coherent beam of X-ray photons. And that wasn't what these were designed to do. It was sort of a side effect, but then they thought, hey, this is pretty cool, we can use this. So they kind of enhanced them for that purpose. And now all these, so these synchrotron facilities are kind of used to do a lot of advanced scientific imaging, because you have a very high intensity beam of X-rays, okay? And you can do imaging of like mice brain, and you can do dynamic imagings of insects flying. Of course, the insect doesn't live very long. And you can image material properties and crystal structures and materials and all kinds of cool scientific imaging, okay? There's also things like, you may have seen, okay, I have to mention it. You might have seen the thing with using the long baseline EHT, the Event Horizon Telescope on the TV, right? And that's an example of a technology where you take that kind of sparse data and you form an image of the first black hole, right? And then let me give you, what are some other examples? There's sort of endless examples these days. And then also in manufacturing. So if you want to inspect, manufactured products, like one of the things that people are really interested in doing these days is imaging integrated circuits. So if you have an integrated circuit and you want to inspect it, you want to image the entire Intel processor to make sure that every transistor is where it's supposed to be and has the correct dimensions. there's techniques you can do for doing that, very advanced techniques. Actually, the method that's sort of the leading contender in that is a thing called tychography, which I don't know if we'll be able to talk about, but it's very interesting. It's an example of a phase retrieval problem, but it fits into the context of what we're going to learn here. And then another example is security imaging, right? So airport security is sort of generic imaging. So there's a myriad of applications for what we're going to learn. But what we're going to learn is sort of the underlying mathematical principles, okay? So to do that, and our emphasis won't be so much on the sensors, although I'll try to throw a little bit of that in along the way because I know that it kind of makes it more interesting and also it makes it more relevant. But our emphasis will be more on the sort of the generic mathematical techniques that are crucial. And I said this last time, but it really can't be overemphasized that the most important thing is to get sort of the core philosophy of how you solve these problems, because it's, for most people, pretty counterintuitive. So the way you go about solving these problems, these computational imaging problems, is not the way that you would naturally do it. I mean, most people who would try to solve a computational imaging problem, their strategy will immediately be wrong, okay? Okay? So, and there's a natural tendency to keep falling back into that approach that's sort of wrong. And the reason that, and I said it last time, but I'll just say it again, because it is so important. It's sort of this, okay? This is sort of the big idea of the class in some sense. Most everything we'll learn about connects to this in some way, shape, or form, maybe a little bit obliquely, but pretty much is important. And the idea is that you have a physical system, and then you have a mathematical model. So the problem is that the traditional way of solving inverse problems that you came out of like classical mathematical approaches is just to analytically solve for the inverse, right? So like I said last time, the classic example is y equals ax, right? So you just say, okay, ax equals a inverse y. The problem is that there's lots of problems. One is that you may not be able to compute a inverse. In fact, usually you can't. The solution, I mentioned it last time, it may not exist. There may not be a solution. It may not be unique, okay? And if it does exist and is unique, it may be unstable. So, okay, but even if that isn't a problem, even if A is a well-posed matrix, okay, it's stably invertible, that computing the inverse A is just not practical for most cases, okay? Because X and Y here are images, or even volumes. So if it's a medical imaging problem, X, and this is another thing that's a little counterintuitive in this class. I'll blank this again. That we think of, okay, one of the beauties of deep learning is it's sort of brought to the fore tensors, which are really powerful. But still, a lot of problems, we convert data to vectors, okay? And, for a lot of reasons. Some of them are practical because there aren't as many tools available for dealing with tensors, just numerical tools, okay? Software. And so you have an image like this, and we convert the image to a vector, okay, by using some raster ordering of the voxels. In this class, for the most part, vectors are always data. And so people will call an image a matrix, okay? I specifically avoid calling an image a matrix Because when I use the word matrix, what I mean is an operator. It's a function. I call this a 2D array of data, okay? Vector I use to mean data. A matrix I use to mean operator, okay? It's an important distinction. So this X here, this is an image, okay? So, or it might even be a volume. So if it has 1 billion pixels in it, which is not that many, because if you have a 1,000 by 1,000 by 1,000 volume, which is not unrealistic for a lot of modern problems. In fact, we get bigger volumes than that. We've done reconstructions for material science problems in synchrotron data where it might be like 2,000 by 2,000 by 2,000. So that's like 8 billion voxels, okay? Then this vector has 8 billion components in it because each voxel in that volume is one element of this vector. Is that clear? By the way, this used to be like super abstract and weird for people, but I think students, this is becoming more and more natural as they get more exposed to these kinds of image processing is sort of percolating. What would used to be the really cutting edge stuff is now kind of commonplace. So, and your data, well, okay, you might have sparse data, but let's just assume that you actually have as many measurements as you have unknowns. So that means this matrix A is square, okay? So in that case, this also has 1 billion. So it's 10 to the 9th and 10 to the 9th. That means that this matrix is 10 to the 9th by 10 to the 9th. So it has 10 to the 18th elements in it, okay? You can't invert that matrix. It's just not realistic in any sense, okay? So computing an exact inverse is just not practical. And then the other thing is this. It's not useful and it's not practical. Because if you could do it, it really wouldn't give you a good answer. And you really can't do it. And then also, if the forward model, this is called the forward model. If the forward model for your problem is nonlinear, which it is in many practical problems, because real systems are often nonlinear. Of course, we don't consider nonlinear systems nonlinear forward models in this class, but it's important. We'll maybe do a little bit of it, but not a huge amount. So if it's nonlinear, then you may not be able to compute in it. There may not be any analytical form to the inverse, okay? So all those things just make it not a very good idea to try to compute the direct inverse, what I call. Now, there are certain important classes of problems where you can compute an analytical direct inverse in closed form. Okay, in my opinion, the classic example is what's called filtered back projection, which is an algorithm we learned about in 637 if anybody's taken that class, okay? So that has kind of a beautiful situation where you can compute an analytical solution to the inverse for an important practical problem, and it gets used a lot, okay? And then there's other algorithms, but they're kind of all sort of similar and equivalent, so I'm going to all refer to them as filtered back projection. So I don't want to be dismissive of analytical techniques, but they all break down when these algorithms only work when you have meet certain pretty stringent conditions. Like basically you have to sample with the Nyquist rate. I assume people know what the Nyquist rate is, right? You have to make certain, I mean, they're pretty limited, okay? Now, that doesn't mean that they're not very, very useful and widely used, but they're not general, okay? So when you want to go solve a much more general inverse problem, you end up, this is a much more general framework. The price you pay for this framework is that a few things. I mean, is there a question? Or? Yeah, is that the computation solving in this way is much higher, okay? But let me first describe what it is, okay? First of all, the thing on the top, that's your physical system, okay? We won't really talk about that explicitly in this class because we'll just assume we have the data. The output of the physical system is Y. That's the data we have, okay? But it's important to keep in mind that there was a physical system out there that produced the data, okay? And then our goal is to recover X. And then we have this mathematical model here, okay? So what you're trying to do is it's like you're trying to solve a puzzle, right? You're trying to find the input to your mathematical model, which produces the output that you've observed. That's a very different way of solving the problem than computing A inverse. It may not seem as very different, I don't know if it does or not, but it is. And I can guarantee you, you will automatically, because it's just like, it's like some kind of brainstem response, okay? It's like if I gave you a steering wheel in a car, if I gave you a car in which the steering wheel was reversed, so if you wanted to turn left, you have to go like this. Yeah, so turn left, you'd have to go like this, and to turn right, you'd have to go like if I gave you like a few months to practice, you could eventually get to the point where you could drive the car just fine, okay? But in the beginning, it would be very bad, okay? I know it would be for me. Maybe some of you are more coordinated than I am, okay? Because it's wired into your brain. And your brain's going to immediately want to take Y and produce X, because that's the goal. It's like saying, I need to go from San Francisco to California, so I'm going to buy a ticket to fly from California to San Francisco. Why am I doing that? But in this approach, instead of taking Y and producing X, you actually do it by taking X and producing Y, which seems totally backwards, okay? And the reason you're doing that is because you're running up trial balloons, you might say. You're producing outputs and seeing if they match. Then you're using the result, you're comparing it, and then you're feeding it back to correct the, it's sort of like a closed loop control system almost, you might think. But the other thing that's super important is this prior model, which I talked about. Because if the problem is ill-posed in the sense that, say, there's no unique solution, or there's an infinite number of solutions, or there's noise, then you really need additional constraints. And so now you might say, what scientists are always taught that they should have pure data, okay? So this part of the problem is very unsavory to scientists, okay? They're like, I don't like that, I don't trust that, I don't know what it's going to do to my solution, okay? And when they say that, I say, you're right, it's good, don't trust it, okay? But here's the problem, you have no choice, okay? Because the problem is this, if you have 100,000 measurements and 1 million unknowns, you have one of two possible choices. You can throw up your hands and you can say, look, I learned in junior high that I can't solve the system of equations. There's an infinite number of solutions, and I can find a solution which is arbitrarily large, any place on this vector space. So I can go to infinity and it's still a valid solution, okay? So therefore, you've asked me to solve a ridiculous question, and I can't do it. And of course, the solution to that, if you're actually solving a practical problem, and particularly if you're working for a company that's trying to make money, is they'll say, well, yeah, that's wonderful, but now we don't need you to be employed with us anymore, okay? Because you've no longer produced any useful solution. So you have no choice. You have to do something, okay? And I would actually argue that you always do this, even in analytical techniques, because you never sample a signal at infinite resolution. You never sample it at infinite. If you're processing something on a computer, you have to sample it at some finite rate. So you're making an assumption about the bandwidth of the signal. Or you're limiting the bandwidth. You're just filtering it. Okay? So you're throwing some of it away. You can't recover it. And so that brings us to this concept, actually, of the Bias-variance. Oh, okay, this is a nice little diagram. So what happens here is that you make some measurements. Let's say in a classical problem for computational imaging, you may have 1 million unknowns, but you only have 100,000 measurements. So you're underdetermined by a factor of 10, right? That means that you have 900,000 degrees of freedom for which you have no answer. The solution could be anywhere in this 900,000 dimensional subspace, okay? So when you have, but real images if I just take white noise, the chance of it looking like a real image is really kind of small, okay? Where small means 0 for all intents and purposes. Like the probability that I'm gonna just generate white noise and it's gonna look like the Mona Lisa, okay, is super improbable. You know, it's like the probability that I'm gonna tunnel through the wall, okay? Well, I mean, that could happen too, but it doesn't usually, right? So what we want to do is model the probability distribution image. Now, here, this is like a 2-dimensional image. Okay, it only has 2 pixels in it. One of the things that you're going to have to get used to maybe, or it would be best to get used to maybe is a better way of putting it in this class, is, and maybe I don't want to scare everybody off, but I think it's good for you, okay? It's a thing I call abstraction, okay? Abstraction. Abstraction is really important, okay? Because if you understand things at an abstract level, you can apply them to a much wider variety of problems. People, I think, tend to, confuse the word abstract with, or at least interchange them with theoretical, you know? And we have this idea that things that are theoretical are not practical, like it's the opposite of practical. But that's not true. Something can be theoretical, something can be abstract and very powerful and practical, and sometimes it can be useless, or it could be just fun, okay? But abstraction means that you see how a general thing can apply to a lot of special cases. And that's a very powerful idea, right? So this is an example of an abstraction, okay? Because we have only 2 pixels in this image, and real images always have more than 2 pixels, okay? But imagine that you only have 2 pixels. So you know all the pixels except for just 1 pixel in the image. If you're only missing 1 pixel in the image, you can replace that pixel value pretty accurately, just intuitively, right? I mean, use the average of its neighbors, right? So I would actually argue that if you know all the pixels in the image except for 1, the uncertainty in that 1 pixel is pretty small. So that basically argues that images live on a manifold in a higher dimensional space. So now, it's not really a manifold because it has some thickness to it. Because there's still some uncertainty to that pixel. But, so consequently, you can get solutions to problems even though you don't have enough data. Because you look for the solution that's at the intersection of the manifold defined by your measurements. Here we're assuming the measurement manifold is linear. It doesn't have to be, but often it is. But the image manifold is always nonlinear, right? Because images are really complicated. You can't approximate them as living on a linear manifold very accurately. I mean, you can do that, and sometimes it's useful, but it's a really rough approximation, okay? So, okay, now, then that brings us to this other really key idea, the bias-variance trade-off, okay? So, bias, okay? So the idea is that, you make a measurement, you have some kind of system, and you measure something, y, and then you have an estimator, t. So you have t of y equals x hat, right? Now, if you perform the same experiment many times, right? So you have, we'll call it y1, y through yn. So you have n versions of the experiment. Then for each of these, you get an x1 hat through an x hat. If you average those, okay, then it's okay. You're sort of averaging out the noise in your experiment, or the randomness more generally. So if you average those results, the result's still not going to be perfect, because there's some systematic error. The other way of looking at it is in experimentalists, they have a thing called precision and accuracy. And I always forget which is which. So if you have the bullseye here, okay? So if you throw the dart, you get a bunch of things like this, okay? The bias is this error, okay? It's the offset from from what it should have been. And the variance is the cluster size. By the way, I heard a really funny joke yesterday. I'll tell it to you. Okay, here's it. I'm a really bad joke teller, so I apologize in advance. But an engineer, a physicist, and a mathematician are asked to put a fence of minimum size around a herd of sheep, okay? Has anybody heard this joke before? Okay, sorry. I apologize right up front that you're going to be subjected to this in this class, okay? But so the physicist, which one? I even forgot what I just said. Oh, the engineer. The engineer pulls the sheep together and then puts sort of a circular fence around them to minimize the length of the fence. The physicist starts with a fence that goes to infinity and lets it contract down until they get a convex hull, okay? And the mathematician just puts a fence about themselves and says that the sheep are on the other side of it. Okay, well, maybe it wasn't as funny as I'd hoped. But anyway, okay, so this is the bias and the variance. So if you're forming an image, the bias usually corresponds to something like blur. No matter how many times you collect the data and reconstruct an average, you could average 1 million reconstructions. You get rid of the noise, but you wouldn't get rid of the blur, because the blur is reproducible. So this is like blur. The variance is due to like noise, okay? So there's a bias-variance trade-off. You know, bias is generally viewed as being more pernicious, like more undesirable, nastier than variance, okay? Because it's sort of systematic, right? But the problem is this. If you want the bias to go to 0 for these problems, so bias would be like blur. If you want to have infinite resolution in your reconstruction, then as a practical matter, your variance goes to infinity. So you have to accept some sort of bias. So, but if you want the variance to go to 0, if you want to have no noise, then usually the bias has to go to infinity. So in other words, you can get rid of all the variance by just smoothing the whole thing, out, okay? You'll get rid of all the noise, but you also get rid of all the detail. You'll have no it'll be all blurred out. So this is absolutely lies at the center of everything we're doing. Machine learning methods are a way of introducing bias to reduce variance. That's what they do. Anybody who says they have a machine learning method that has no bias, okay, either isn't really doing machine learning or doesn't understand what they're saying, okay? Because that's what they do. Now, and that's one thing that's a little bit, people are worried about that with machine learning methods, because that's what they do. They introduce bias. So you want to be able to at least control the bias you get. So the thing with the methods we are doing in this class, which are essentially machine learning methods for the purposes of reconstructing images, is that we want to operate on this bias-variance trade-off. But at least we want to get you say, well, okay, I can't, asking for no bias, which is what the physicists would say. They'd say, well, I don't want any bias, okay? I want perfection. The problem is perfection has infinite cost, and nobody has an infinite amount of money to pay for it. So you have to accept the bias. So that's this idea that when the physicists say, I don't want any prior model, you say, well, you have no choice, really. I agree with you. It's not a good thing. I don't like it. But what is it here? You take the prior model, and this is what you do. But you have no choice. You have to have this bias introduced by the prior model. So you have this prior model, P of x, and you have everybody staring at it. You go, okay, I don't trust you. You're dangerous, okay? So the beauty of my argument is with these methods is that you put your biases up front and center where you can keep an eye on them and make sure they're not screwing you up and giving you incorrect answers to your questions, problems, okay? And this is an example of how you can get better reconstruction quality on problems like CT imaging, okay? This is, this table here, okay, we're going to talk about Gaussian models. Gaussian models are the simplest models to analytically to deal with. We'll talk about non-Gaussian models. That becomes much more realistic. And then we're also going to talk about discrete models, and we're going to talk about them in 1 and 2D, and we're going to talk about them as causal and non-causal. So the most important, the most practical case is that, well, okay, 2D and ND. 1D is distinct from ND for n greater than or equal to 2. And the reason it turns out this is that in 1D, topologically is distinct from higher dimensions, because if you remove a point in 1D, you disconnect the line. If you remove a point in 2D, you don't disconnect the plane. It's topologically, it turns out that that's critical because it changes everything, basically. See, things are still connected here, okay? So it changes everything. So that's one of the things we'll talk about. And then later we'll talk about more sophisticated techniques that more sophisticated models based on things like like deep neural networks or whatever. Okay, so I first want to talk about probability. And so everything, oh yes, question.
Why do we care? So we talked a lot about why we wanted to model, I think it was Py given x rather than Px given y.
Right.
Why do we care about either one? Like, I mean, if you're going to have a model anyway, is there a reason why we would want to do one direction over the other? Because you could just... Yeah.
Right. No, that's an excellent question. And there's a role for both, really. So y is always used for the data, and x always used for the unknown. So Py given x, this is what's called the forward model.
So you don't have data, you don't observe x?
No.
Okay.
That's one of the things that's really, you have to get used to. That you're talking about the distribution of something that you haven't observed, right? Or that you're talking about the value of something which you've never seen, okay? Okay, so this is called, P of x is called a prior in a Bayesian framework, okay? This is always a well-defined concept. It may be that I'll use the same notation even when x is on a random variable or isn't assumed to be a random variable. But you're also talking about P of x given y. This thing shows up real commonly in machine learning because in a lot of applications of machine learning, you just train some machine learning algorithm to estimate the thing you want to know from what you have. But P, this is related, this is the posterior distribution, okay? And Bayes' rule is what relates these two, okay? So Bayes' rule is what relates these two, so that P of x given y is equal to P of y given x times P of x, right? Divided by a constant, where the constant is P of y. But you don't really often need to know this constant because you know that P of x has to integrate the 1. Okay, so the advantage of using, and this is sort of the viewpoint that we'll usually take in this class. And the reason is that, and that's why this class is more oriented towards physical sensing problems, you might say. Because in a physical sensing problem, you often have a detailed model for this forward model. Now, if you're trying to estimate the average number of hamburgers a person eats from their Twitter feed, okay, then you might just go for this, okay? Because you don't have a really detailed physical model that's broadly accepted for the relationship between the number of hamburgers you eat and your Twitter, okay? But, and the way you Twitter, okay? I mean, such a model probably could be formulated, but it doesn't like fall out of some simple mathematics. So if you're gonna model this and it's so complicated, you may as well just go right to that. But there are issues associated with going right to this. Because when you go right to this, you can't control your bias-variance trade-off, which is actually a big problem with machine learning algorithms. You get whatever the bias and variance is that results from the minimum loss. But you know, that may not be, your loss function doesn't necessarily count. Bias and variance is complicated, okay? So, okay, so that's a good question.
So the setup basically is the premise for the...
Oh, no, we're okay. I'm paranoid because of the time. I don't want to, go on.
Yeah, no, so the premise for the course is that we observe y and we don't observe x, and we want to infer x from our y.
We want to infer x, yes. You just hit the nail on the head, okay? I mean, like, the entire 2 classes are my heart is going pitter-patter, okay? Because you just said exactly what I'm trying to communicate, okay? And it sounds like such a simple idea, and once you got it, okay? But it's really a hard thing, and it'll leave you, okay? I'll warn you, okay? Okay? And they'll come back, okay? By the way, one thing, because we're kind of running out of time, but this was a great way to end up the class, I think. And we took a little more time on the introduction, but, you know, hey, you know, we should enjoy this semester because it's the pandemic edition, right? Yeah. I mean, it's a little smaller class. We can have some fun. But I noticed that the class after this was kind of big. So here's what I was, and you know, I felt last time, I was a little disappointed that we couldn't have like, you know, a little conversation with it. I like to talk to students after class, right? So here's what I propose. Maybe what we could do is, if people have questions, we can meet outside the doors over here. That way we can enforce all our social distancing, everything, and so forth. And if you want to ask questions, we can talk out there, okay? Okay, that way we get out of their way for this classroom. All right? And then we'll talk. I'll see you on Friday. Oh, I should also say one other very important thing that I'm going to super emphasize next time. You got to read the notes, okay? I know it's like painful, but you've got to read them. You got to read them. You got to read them. You got to read them. It's like super, 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 super important. Please read chapter 2, okay? I'm not just kidding. It's not like, oh, read the chapter and do the problems. No, really read it, okay? It's actually more important that you read the chapter than you do the problems, but do both, okay? Because it's really important that you kind of start getting your head wrapped around the notation and things like that. And if you have questions, ask it, because it's a small class, okay? All right? All right. So maybe we should leave so that we don't interfere with the next class. Oh, are we out? Or is maybe my phone, my watch is behind, or ahead, or something. I'm not even sure what time it is. What time is it?
18.
Oh, we actually have a couple more minutes. Okay. But anyway, go on.
Is the homework that was assigned due on Friday?
In theory, yes. So, I mean, you don't have to actually hand it in, but you should have it completed. Okay? And then we could actually kind of go over things if you want, too. I mean, I won't actually grade your homeworks, but I may collect them. If I do collect them, and I probably should collect them, maybe actually hand them in if you can on Friday, okay? But if I collect them, make sure to keep a copy. Actually, it'd probably be better if you, oh, you're not supposed to turn in paper. Oh, right. So, okay, I'll give you the instructions. They're actually on the website. There's like an email address I have students email to a Gmail account to collect PDFs. So scan it. So keep a hard copy. Keep your own copy, okay? Because you'll want to refer back to them at the exam and the study and things like that. After you put a lot of effort into working some problems, you don't want to lose that, right? Because it'll help jog your memory when you want to remember how to do various calculations. All right? So then I'll see you next time. Thanks. This was a little more fun than last time. I felt last time maybe my glasses were fogging up a little too much.